This is a video to help explain the physics concept of Compton scatter, an assignment in Radiation Therapy, Physics 1 at OHSU by Alicia Hurd. To fully understand Compton scatter, it is important to know that electrons are arranged in shells around an atom's nucleus. In Compton scatter, the bombarding photon interacts with the atomic electron. The photon collides with the electron, losing some of its energy, and is deflected from its original path. The electron absorbs some of the incoming photon's energy and is then ejected from the atom with significant kinetic energy. In this interaction, the energy of the incident photon is much larger than the binding energy of the electron. That's why Compton scatter looks like a collision between the two particles. Just to clarify, let's talk about a couple facts. Fact number 1. The photon isn't absorbed in Compton scattering as it is in the photoelectric effect. Rather, it is deflected. Fact number 2. The incident photon cannot transfer all of its energy to the electron in a Compton scatter interaction. The energy of the scattered photon is never zero. Now let's talk about how we can determine the energy of the deflected photon in a Compton scatter interaction by using this equation. I realize this equation can look a bit scary, so let's break it down. This capital E is the energy of the scattered photon. It is the value we are trying to find. Both of these capital E's are the energy of the incident photon. m naught c squared equals 0.511 MeV for an electron. And finally, theta is the angle of the scattered photon. Let's go through a practice problem together to make sure we know how to use this equation. A 1.22 MeV photon undergoes Compton scattering by an electron through a 70-degree angle. Question number 1. What is the energy of the scattered photon? We know that E equals 1.22 MeV, m naught c squared equals 0.511 MeV, and theta equals 70. When we work through this equation, we find that the energy of the scattered photon equals 0.47 MeV. Question number 2. What is the energy of the scattered electron? We can find this value by subtracting the energy of the incident photon and the energy of the scattered photon. For this problem, we find that the energy of the scattered electron to be 0.75 MeV. Compton scatter is the most important interaction in tissues at diagnostic therapy energies because this interaction is most likely to occur in soft tissues in the range from 25 keV to 10 MeV. Why does this matter, you may ask? After the collision of the incident photon and electron, the photon that is deflected creates scatter radiation. This scatter radiation creates an overall darkening on X-ray film, but not in a way that provides useful information. The scatter radiation delivers misinformation to the image receptor, which fogs the film and decreases image visibility. Higher density tissues such as bone tend to absorb a higher amount of X-rays, which appear white on film, whereas low density tissues that contain air, such as the lungs and large bowel, allow greater penetration of X-rays and appear black on film. Water density tissues such as muscle, blood, and solid organs create the greatest amount of scatter radiation in the body. When these tissues are imaged, it will be harder to identify because of the blurring created by the scatter radiation. Thanks so much for watching. I hope you learned something awesome about Compton scatter.